What?
And a centrifuge is the, it's like this is the center.
Okay,
I
so
think it's-
let's talk about the centrifuge problem.
Okay, that's,
Okay? Caitlin, can you see if they can see this in
No, they can.
the, okay? So you have the center that it spins about.
uh-huh.
Then you have the test tubes, but the test tubes sit in here like at an angle. Some of them spin out flat like this, but the whole point being is that this spins really, really fast. So if I get this going, okay?
Sounds like my AC, right?
Okay?
Oh,
So
no, it doesn't.
all that's doing is creating a very, like a false gravitational field, okay, because it's spinning so fast. So there's two things you know when things spin fast. Number one, you make a lot of revolutions per second, which means that it has a very, very high frequency, but the period for one rotation is really, really small because it's spinning so fast. So if you look at what's happening on that problem on number 10. So what I'm saying is that here's the center spin axis. The edge, and this is like the edge from here to the test tube, okay? So the test tube is going to sit in here like this, okay? So that distance is 5 centimeters, okay? Then the test tube is going to be here. So you need this distance from the edge of the test tube to the bottom of the test tube. So you know this is 100 millimeters and this is a 30-degree angle. So you're trying to find the side opposite of 30 degrees. And the 100 millimeters is like the hypotenuse. Okay? So you work some magic, that's 50 millimeters. Sine of 30 times 100 millimeters. So you got 5 centimeters to here, you got 50 millimeters to here. You need that total distance. Add the two numbers together.
I think it's like,
Huh?
I think it's like,
Just,
Maybe like 10.
y'all can add, okay? So then, that's part of it. Then you're told that it's spinning at 4,000 revolutions per minute. Okay, cool. So 4,000 revolutions, and I would put that over 60 seconds, okay? Because you can't work in minutes, it has to be in seconds. So when you do that, because that's revolutions per second, is that frequency or is that period?
It's frequency.
It's frequency because it's revolutions per second. So at this point, you have a decision to make. So when you take 4,000 and divide it by 60, Caitlin, you might spin that so they can see that board again.
66.7.
What was it?
66.7
Say 66.7
seconds.
revolutions per second. So here's the decision that you need to make. So you're trying to find what's the centripetal acceleration. So one option is that you could use 4 pi squared r over t squared. But then realizing this is frequency, you got to take the inverse of that to get the value of t, okay? And plug it into that. If you're a fan of capital T's, hey, I was president of the capital T club. Great, do that. The other option is that you know that since period and frequency are inverses of each other, that also becomes 4 pi squared r over 1 over frequency squared, and that frequency squared flips up, and then you get 4 pi squared r times frequency squared. So I don't care which one you do. It's a personal preference, okay? So when I did it, I just did this because then I didn't have to go through the hassle of taking the inverse of 1 over 66.7 and mucking with that. I don't care. But here's the point on 10A. So on 10A, on that one, you're trying to figure out the centripetal acceleration, okay? So on 10A, that should be a pretty big number, like something times 10 to the fourth, okay?
Positive fourth or negative fourth?
It's just there's no way you can get a negative number out of this. There is nothing that's negative.
Oh, okay.
No, he meant.
He was asking you if it was 10 to the negative 4, so yes, it's a large number.
Oh, no, it's a big number,
Oh, okay.
big number. Now, on B, you want to figure out how many G's are you pulling, okay? So, this is what we talked about yesterday. Go away. So, to get G's, and this is something you got to be able to do on the lab today, you take your whatever that centripetal acceleration is, and you divide it by 9.8 meters per second squared. So, you're going to take whatever that answer is, 2,000 meters per second squared, or whatever that is, and then you're going to divide that by 9.8 meters per second squared. The meters per square cancels out. Boom, you're left with just G's, because it's just a multiple of that. So, both of your answers on number 10 should start with a 1 and a 7.
Shucks. I'm confused how you found the radius. Because wouldn't it be sine 30 times 0.1, not times 100? Because
Well, I just left it as millimeters.
we don't need to convert it.
No, you do. Okay, you absolutely do.
But that would change my answer if it's converted, wouldn't it?
Because this is a montage of units. You've got this in centimeters,
Mm-hmm.
and you've got this in millimeters. You need to convert all of those into meters,
Yeah.
and then add them together.
Mm-hmm.
So what'd you get when you added them together?
Well, for the bottom one, I had 0.05 meters.
Yeah,
And then I guess it would be, I don't know.
My numbers are starting with an 8.
no.
So, that just means that
Okay,
you did it wrong.
Caitlin, so you got the 5 centimeters, right?
Mm-hmm.
Divide that by 100, that's also 0.05.
So it's just 0.1?
Yes,
Okay.
Actually, no.
I think I just did my math wrong or something.
yeah. Your answer to, let's talk about number 11. So, there's a couple of ways you can find out the velocity of the spinning ball as it goes around. One option is that you literally turn it into a projectile. So I've got this swinging around like this, okay? As soon as I let go of it, it turns into a projectile, okay? It's a lemming problem. So what's happening on number 11 is that you're spinning this thing around like this. Boom, it goes flying out like this. So you know how high it is above the ground, which in this case is 1.80. So you're going to use that to find the time. It's a lemming problem. If you don't know how to do lemming problems, go back and look at all the stuff we did with lemming problems, okay?
That's what I did.
All right, so you're going to find your time. Then you know how far it lands from the point that it breaks, which is 4.4 meters. There's your range, okay? So you know how far it goes, and you know how long it took to get there. And you know range equals Vx time. There's your range, 4.4. You can find your time because you know how far it falls. Then you can find your Vx. So your Vx is how fast the rubber stopper was moving around in the circle before it turns into a projectile. Once you get that, then your centripetal force is just mv squared over r. So if all goes well on number 11, when you're trying to find the tension, which is the centripetal force, that answer to number 11b should be something very close to your age. Not mine, your age. Okay. Your answer to number 7 with the Earth, the centripetal acceleration of the Earth, that should be a really small number, okay? Like 10 to the negative third small.
That scared me. I thought I did it wrong.
No, that's okay. We don't want a big acceleration, because if the Earth does have a big acceleration, we would feel it.
Oh.
Okay.
Yeah, I got that one
Seriously?
done, and then like 5 minutes later, I'm like, Oh, it should be a little number, because then we'd be like
Wait,
sucked
so
into the
is
sun
any-
and just be
Yeah,
dead
it's okay
about
that that's a small
a
number.
billion years ago.
So, is any planet in our solar system like have a big acceleration where we would feel?
Mercury does, because Mercury has the biggest centripetal acceleration because it's moving,
Oh, okay. Close.
it's closest to the sun and it's moving fastest.
What is the lowest?
With the
Pluto.
furthest one out, well, Pluto, because I consider Pluto a planet.
Just stuff further.
Okay.
Pluto. What's your issue? Where does it find out?
Let me give you some hints on the problem out of the book. Where's my book? So let's talk about problem number 10.
Oh my gosh. Like page 18410?
Yeah,
Oh, that's another something. Correct.
that's the wind turbine problem, right?
Yeah. I have no
Yes.
idea how to do that. I read it, went to bed. No, I'm just kidding.
When asked
I
like
didn't
that,
do
should we
homework.
give it in revolutions per second? Or
I don't care, that
Okay.
works. Okay. So here's this wind turbine. Obviously, they work because they spin. Wind turbines that don't spin don't generate very much electricity. So, you know there's 40 meters long, okay? So there's your radius. And it spins at 17 RPM, okay? At what rate should the blades, the offshore rotate, the speed of the tip is be the same as that of the turbine on land? So there's a couple of ways that you can do this. Number one, start with the 17 revolutions per minute, right?
Indeed.
So one option is that you just work in this number. You go, okay, hey, 17 revolutions per minute. So since it doesn't technically ask for like what units, it says at what rate should the blade spin. That could be in, the easiest thing to do is just have revolutions per minute because it just asks for a rate function. So with this one, and you're told that the ones offshore are twice as long, okay? So those are going to be 80 meters long, okay? They're going to be twice as long. So one option is if you look at this and go, okay, right. So your centripetal acceleration, if you wanted to find it, there's a couple ways you can do this. One is you could find the, or you could use 4 pi squared r times frequency squared. And you could find the centripetal acceleration, okay? You could. I'm not saying that you have to, but that's an option. So then, knowing the centripetal acceleration, then you could go, oh, centripetal acceleration equals v squared over r,
Oh,
okay?
I like this. Good work, Mr. Burkamp.
I'm just telling you. Now, the simpler way to look at it is if you just think this through, is that just think about this. If this is twice as long, okay, this is just the easiest way to think about this. If that's twice as long, right, and you want it to have the same speed as the 41 does, think about this in terms of like a NASCAR race. Here's the car on the inside. Here's the car that's out here on the outside. Okay, so basically this radius is going to be much longer. So if you want these 2 points to be moving at the same rate, okay, and that's the whole key to this. It says you want the rate should, if the speed of the tip is to be the same as that of the turbine on land. So if you have this really, really, really long blade and it's spinning at the same rate, that's going to be going really, 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 really fast because it's so far from the center. You want this point here to be going the same speed as the shorter one. So if you think it through, it's like, okay, right, that's got to be going slower because it has such a bigger radius. So the easiest way to think about that is, okay, well, if I make it spin half as fast because it's twice as long, it's going to have the same speed. because of the fact that that thing is like twice as long. So if you look at this in terms of like a rubber stopper, so if I've got like a radius like this, okay, right, that's traveling at a certain speed. If I make that radius longer than to have that same speed, I need to be having it going half as much because of the fact that I've doubled the radius. So to get the same speed, I'm going to slow it down. So the easiest thing to do is just take 17 and divide it by 2. And there's the easiest way to do it. Because it really does, you could have it in revolutions per second, you could have it in revolutions per minute. It really doesn't specify.
184.
So I just work in revolutions per minute and take the 17 and divide it by 2 and boom, there's your answer.
This one.
So there's that. Let's talk about number 13 and how I do not want these answers done. So on question number 13 says, rank in order from largest to smallest the tensions T1 to T4. This is what I do not want on a question like number 13. I don't want like random things where you put like 3, 2, 4, and 1. I have no idea what that means. Okay? I don't do commas. I do greater than, I do less than, I do equals to. Okay? So when you answer a question like number 13, you're going to see more and more questions like that, where you rank things. Commas don't mean anything. Okay? So let me give you a hint. Your answer to number 13, that first value should be number 3. Okay?
So Dylan, you're actually wrong.
That should be number 3. Now, let's talk about question 10 with the spinning satellite. So, you create artificial, because one of the concerns about traveling in deep space is deterioration of bones and muscles. Because you're just floating around, you're not lifting weights because you're in zero gravity. So one option is that you make it spin, okay, like this.
What question?
Uh-huh.
Number 10.
No,
The
no,
first-
I'm talking.
The one with 3 in there.
The one that says, talk about the spaceship. So if you look at centripetal acceleration equaling 4 pi squared r over t squared. So if you look at what's going to happen, if this is the inside of your spaceship as it spins, every point on here is going to have the same value of period, because it's all going to spin at the same rate, just like we did with the quarters yesterday.
Oh.
They're all going to spin at the same rate.
Oh,
So
okay.
t is the same. So to create a bigger centripetal acceleration, which is what you would feel, okay, because if you're on that outside and you're moving around, obviously, since it's 4 pi squared r over t squared, if you want a bigger centripetal acceleration, what do you need to do with the radius?
Make it big.
Make it bigger, okay? There you go. All right, any other questions?
I think I'm ready to turn this one in.
Your answer to 4 on the problems I typed up should be 4.
Oh.
I did not get that.
Oh. Yeah, you did.
For what?
3.9.
Your answer,
Okay. That's 4, buddy.
On number 4, it should be 4?
yes.
Am I
I
stapling
did
this
that
to
one
this?
right.
Wait, yeah, attention.
Wait, what did you say number 7 from the worksheet should be around?
Like 10
Something times 10 to the
third.
minus third.
But you didn't give us the number. Okay.
No.
That's right.
But if you got 10 to the negative third, odds are you did it right.
Okay, I did.
Okay, anything else? Going once, going twice?
Your work goes to the right. Your
Yes.
goes to the left.
Now, y'all are beginning, not just you guys, it's both classes. When you staple it, make sure, like especially if you have like multiple pages or something, when you staple it, make sure it's in the correct sequence, okay? Like a couple of years ago, I literally threatened the class. I said, I'm gonna grade whatever sequence you have based upon my answer key. And that's how I'm gonna grade it. And if you have yours in the wrong sequence, you are going to miss every point because every point does not match up with my sequence. So
Yeah.
make sure when you save for it, like I flip that page over, I see the questions, then I see the problems, okay? And no frizzies,
It's gone.
Yes, sensei.
okay? Anything else? Go once, go twice, sold. Okay, then stop the on camera for a second.
I'm assuming you don't want the yellow paper.